Alright, welcome back. So today is going to be the last lecture. We're going to continue talking about reinforcement learning, which is the subject that we started yesterday. And today I'm going to talk about one of the most famous algorithms that people use to solve these reinforcement learning problems. It's called Q-learning. And all of these recent advances that, like if you read papers by DeepMind, and they show these really amazing results of like these things learning how to play video games and control robots, cars, that's all a variant of this Q-learning algorithm. It's a combination of Q-learning with your CNNs, basically. So just to remind you what we discussed last time, the idea of this reinforcement learning problem, again, this is a problem, like this is not an algorithm, this is the definition of the problem. It's this setting where you have a loop, where there's an agent that interacts with an environment. So initially it observes what is the state of the environment, and the definition of the state is a vector with all the information that is required, that is needed for the agent to select a correct action, a good action at that point. So the agent observes the state. Based on the state, it selects somehow an action, and then how it's going to select the action, we're going to see that in more details. It executes that action. And the execution of the action has two effects, like it causes two things to happen. The first thing that happens is that the agent is given a reward. A reward is just a number. It's a real number that evaluates how good that action was at that given point in time. Okay, so it doesn't mean that that was the best action necessarily. So for example, right now, maybe if you start drinking wine, you're going to get a reward, which means that it's really good right now. It doesn't mean that it's good in the long term. So a reward is something that evaluates an action immediately. And based on this reward, the agent needs to somehow adapt, right? It needs to change its behavior so that in the future it can get more reward. But again, not only reward at any one specific point in time, but the total reward that it wants to get over its lifetime. So it's the sum of rewards that really matters. So this is the RL problem, right? And then I gave a few examples of like, this is RL. You give rewards when the thing manages to flip the pancake. The state is all the information that is required to control the arm of the robot. So in this case, the state is basically a vector with the current configuration of the arm. Adobe, Google, Amazon, all these guys are applying RL for the digital marketing problem, which is the problem of selecting ads for different users. So in this case, the state is a vector containing all the information that you have about a given user, and the actions are the different ads that you can show. And the reward that you give to the agent, the algorithm, is +1 if the user clicks the ad, and 0 otherwise, and so on. So we studied, the first concept was this idea of a value function, right? So the value function takes as input a state, could be like one situation in a game, and it tries to evaluate from this state if the agent takes all the actions perfectly, never makes any mistake, so the optimal behavior. Under that assumption, what is the total amount of reward that the agent can get in its lifetime if it starts at this part of the game, at this state of the game? So this is the value function. And then why is this useful? Because then you can, for any particular state or situation in a game, in a video game, you can guess, well, how good would it be for the agent to be in that situation? If the value of that particular state is high, that means that if you can get the agent to that state, because the value is high, that means that from that state the agent can take some sequence of actions and get lots and lots of rewards, which is the point, right? But then, well, it's kind of hard to compute, like empirically compute this if you just look at the sequence of states, because then you have to take into account all the possible outcomes of different actions and so on. So the nice thing is that there is this equation called the Bellman equation, which we saw briefly last time, which is this equation. I'm not sure if everyone can see this. Is this recording now? Good. So the value of a state, according to the Bellman equation, can be computed in a recursively way. So if you look at this equation, the value depends on the reward, the first reward that the agent gets at that state, plus, and this other term is like the sum of rewards from the possible next states. So here we are summing over S prime. S prime are all the possible things that may happen after I leave this state. I take an action here and I go somewhere. So this is the expected, like it's the average sum of rewards that follow from the current state of the game. So it's the current reward plus all the reward that follows. That's the value according to the Bellman equation. Does anyone know who Bellman was? Have you guys studied dynamic programming? One way of, there's one person that studied. Anyway, so like there's a bunch of problems in computer science that you can solve with a class of algorithms called dynamic programming algorithms. And they're really important. Like for example, if you're trying to find the shortest path between 2 points, there are many algorithms that are dynamic programming algorithm, and this guy invented that also. So anyway, it's just important person. So that's the Bellman equation. There's a variant of that Bellman equation, which is actually what we're going to use here in the Q-learning algorithm, which is this. So if you look closely, they sort of look the same. If you look like from far away and don't pay too much attention to the details, they sort of look like there's an R, there's a max, there's a summation. What is the point of this? So this equation, this Bellman equation, is measuring something a little bit different. What this is measuring, again, this is also a number, it's a real number. What this is measuring is if the agent starts in this state of the game, some state S, could be like the agent is in one specific position on the screen, and the agent executes this action, A. It could be the best action, it could be a terrible action, we don't know. But given that it was in this situation and it executed this action, this function is going to return the total score, like the total reward that the agent expects to get from that point until the end of the game. Okay, so this is like, if you imagine that, again, video games are, I think, a good analogy. If you, like the agent is born in one specific part of the game situation, and it executes this action, and then it performs optimally, like it selects all the actions in the best possible way, this is the total score that you expect you're gonna get during that level of the game. Does that make sense? What this number is? The total score that the agent expects to get. Yes? More or less? Okay. What? Do you guys have any questions? I'm not sure people. Yeah.
I am a little curious as to how all these possible states, are they predefined? How do we predefine them?
Right. Okay. So that's a good question. So if you are in one state of the game and you take this action, many things could happen depending on the game. Right? Maybe you decide to jump, but then something happens, like someone shoots you and then you die. That could be one outcome. Maybe you jump and you get a coin. So there are many possible outcomes. In theory, all that is modeled by this function. This is the probability of going to one particular next state, S prime, given that I was in this state and I executed this action. So this is like a model of the game. Imagine that if you're actually implementing a game in a computer, this could be what the physics engine does. You take like the current state and you apply a force to the character, and this thing determines what is going to be the next state of the game.
So the state could be the position of your character, for instance.
Exactly.
Okay.
Yeah. It could, again, the state is anything that is required that the agent needs to know in order to identify what is the best action. If the agent needs to know its current position, then that's part of the state. It could also include the position of the enemies, how much life points you have, so everything, right? So I'm not going to go into details about this, but one key point is that here, in order to compute this total score, we sort of assume that we know how the game might evolve. Like we assume that if I know in advance that if I'm in this state and I take this action, I know what are the possible results. And usually we don't know that. Like the first time that you play a video game, you don't know exactly what happens if you jump at a specific place. Maybe that's a good action. Sometimes you die. So most of the time we don't know about this kind of stuff. You don't know in advance what are the possible results of your actions. But the cool thing is that Q-learning doesn't require knowledge about this. You don't need to know how the game works in advance. You can just learn by actually trying different actions and playing it many, many times. And eventually you figure out, even if you don't have a model of how the game works. And we're going to see how that works in a moment. But the key insight here is that there is an equation, which is this, the Bellman equation, that measures this. It's the total, if you imagine again, the analogies with a video game, if the agent is born in one specific situation of the game and it executes a particular action, this thing, if you could compute it, would tell you the total score that you expect to get from that state on until the end of the level. That's the thing that you need to remember. Okay? So, as I said, to really compute this equation, you would need to know all these quantities, right? Because to evaluate the right-hand side, you need to know this thing, you need to know everything else. But we don't know any of this in practice. We don't know how the game works in advance. We don't know anything. So what happens is the Q-learning algorithm allows you to incrementally estimate these values. It allows you to incrementally, as the agent plays the game, to incrementally improve its estimates of how much score it can get from that state, from any situation in the game, whenever it takes an action. Yeah.
Why do you get the reward for being in the state you are already in? The R parentheses S? Why do you get the reward for that? For just being?
So this could be, for example, this is a kind of like generic formulation. It could be, for example, if the state that you are in is a state where the current position of the agent is the same position where there's a coin, that means that you're going to get the reward for that coin.
Okay.
So the state, it really includes everything that could, for which you could reward the agent.
I think the idea is you don't give rewards for actions because you could have probabilistic events like wind that breaks your way, so you don't get reward for taking the action but ending up in another state.
Yes, that's a really good question. So what he asked, in case someone could not hear, is in many situations the more natural way of modeling the reward is not so much for being here, but like if I'm in some state and I take an action and I end up in one specific thing, like the action is successful, right? I think that's what you mean. Then you get a reward, and it's exactly equivalent to this. There's an equivalent Bellman equation where the reward function is given that I was in some state and I executed some action and some particular event happened, then I get a reward, or maybe then I don't get a reward. You can write the Bellman equation like that, and it's equivalent to this. They can be rewritten. Right? Okay, so the Q-learning algorithm really is just this. This is like the update equation for incrementally updating your guesses, your estimates of how much total score you can get, and it's based on a few quantities, and which are the variables that are part of this equation. So what happens? Can you guys read this? Is this too low? Yeah, I should move this. I was not planning for that. But so what happens is the agent is in some state S, and it picks an action A. Okay, so this is the state of the game, some game screen. You decide to jump. Then maybe when you jumped, you picked a coin, and you get a reward for that. And you observe what is the next state. So the next state is like the next screen of the game. The next image that is showing up on your screen could be that you're now on a platform or you fell on a cliff. I don't know, it could be anything. So these are the four variables, the four things that we need in order to plug those values into this equation and learn. That's all Q-learning requires. Where you were, the action that you executed, the reward that you eventually did receive or not, and what was the outcome, what is the next state, the next thing that happens in the game. And based on that, you just plug those numbers into this equation. So let's see what this equation is really telling us. I was in this state and I took this action, right? And what I want to know is, if I am in this state and I take an action, how much total reward I expect to get until the end of my life, until the level is over. So that's what this number is telling me. So this update equation is, there are two terms here. The first term, it's a combination, right? It's like a weighted average. Alpha is a number from 0 to 1. So like, it's the current guess of how much score I can get. So like, imagine that alpha is 0.9. Okay, if alpha is 0.9, it's like the new value is going to be 10% of the current guess plus 90% of this other thing. So you're slowly moving your current estimate. There's a small weight here, and there's a larger weight to this other thing. What is this other quantity? Well, it's the reward that you actually got by taking that action, and then this other thing here. Does anyone have any idea what this means? So remember, I took that action and I went to some other state S prime. What is this? Like, ignore the gamma. Like, what is this telling me? I'm taking the max over all possible actions that I can take in the next state. Right? So when I consider the next state where I ended up, and I check all the possible actions that I could execute in the next state, what is this max telling me?
The state that will give you the greatest reward?
Not the state, the action that is going to give me the largest reward. So this quantity here means, well, I know for sure that I ended up in this state S prime. From S prime, what is the best thing that the agent can do according to its current knowledge? That's what this is saying. Like, if I check all possible actions A prime that I could select in this new state that I ended up in, what is the best action? In the sense that it gives us the max value of Q. So this thing here is going to tell me from this new state, what is the best, like the largest amount of reward that I think I can get. And then what is the intuition for this summation? Is the reward that I got plus the maximum reward that I can get in the future. So this is my new estimate of the total reward that I can get, right? It's the reward that I got at this time step plus the total reward that I can get from the next stream on. Does that make sense? Okay, so this is the Q-learning algorithm. It's just that. And it's a loop, right? It's like an interaction where you see the state, you see the action, you get a reward, you observe the next state, you evaluate all of this, and then you compute the right-hand side, and you update your estimate for the total score that you can get in this situation. And then what happens? Well, then you repeat the process. You are now in this state, and then you do the same thing. Given that you are in this state, you somehow select which action you're going to execute, you get a reward, you go to a second state after that, you update this, and you keep repeating that. Okay, so let me show you an example of how this works on that game that I described last time. Again, this is a simple maze where the agent starts here. It has 4 actions that it can execute. It can go up, down, left, or right. And the actions are stochastic, so sometimes they fail. If you decide to go up, with 80% probability, if you decide to go up, you actually go up. But with 20% probability, that action fails, and you either go to the left or to the right with equal chance. And if you end up in this state, you get a +1 reward. Here you get a -1. In all other situations, when you take an action, you are punished a little bit. You get a -0.04 reward. That's the game. Okay? So let's see what would happen. How would you apply Q-learning to this game? You start by, so this Q function, this value, is usually implemented, it's stored, when you implement this thing, as a table. They call this a Q table. It's just a table where you have, for each possible state of the game, you have 1 row, and for each possible action, you have 1 column. So just like a spreadsheet. And then you keep updating different cells of this table, depending on what you do. So here, I'm not really showing the table, but I'm just showing that for in each one of these possible states, the arrows denote the possible actions that you could take in these states. So here it could go up, left, right, down, and so on. And what I'm going to do is, for each one, right next to each one of these arrows, I'm going to write down the Q value for this action when the agent is in this state. Okay, so for example, let's say the agent is in state 2-1, which is this, so row 2, column 1. We would have 4 Q values associated with that state, because we have 4 actions that we could take in that state. And again, just to remind you guys, what is the intuition about this? The Q value of 2-1 and action up is basically like the preference, how good the agent thinks it would be to execute action up, given that it's in this state. And what do I mean by preference? This is actually a number that estimates the total score that the agent can get if it starts here and it goes up. Same thing for all the other actions. So how do you select an action if you have access to those Q values? Let's say you are in some state S and there are 4 actions, A1, A2, A2, A3, and A4. These are 4 numbers. So this is the total score that I can get if I assume that I'm executing A1. This is the total score if I assume I execute A2, and so on. So to select the action, you just compare these 4 numbers, and you select the action that has the largest expected score, the largest Q value. So it's just this. I do the max over all the possible actions at a given state, and I take the check which action has the largest Q, and that's the action that I execute. Okay, so far? Good. So how do we start running the algorithm? Well, we start by, this is the domain, and we're gonna initialize these Q values. We don't know, we have no idea the total score that we can get. So what do? We just pick random numbers, or 0, or it doesn't matter. Here I'm picking random numbers, just to make things more complicated. So here, like in this state, like what Q value is this one? This is the Q value of what state and what action. That is the Q value of state 3, like row 3, column 3, and action left. So this means that given this random initialization of Q, the agent believes that if it is in this state and it takes action left, it can collect a total score, total amount of rewards of 4.2 rewards. Accounting again the reward that it gets here and all the other rewards that it's going to get in the future. And maybe this is completely wrong actually. Actually, this is a good question. Is 4.2 a realistic number, a realistic reward that it could maybe get? Yeah.
Well, what seems weird is that 4.2, like going left there is higher than going right.
Yeah, because these are random numbers.
Yeah.
They are crappy numbers. These numbers are completely wrong. You're right. They after you learn the algorithm, they're not going to look like this. So, is there any way that you could get 4.2 rewards total if you start from here? No, right? Because every action that you take here, you're penalized a little bit by a minus 0.04. And the largest reward that you can get is +1, so it has to be less than +1. This is completely wrong. Everything here is completely wrong, but that's the point. Now the algorithm is going to slowly improve these crappy random values. Some people initialize everything with zeros. Maybe that's not so stupid, but anyways. So let's say the agent is here in this state, 3, for some reason. Given the current knowledge, so we could compare, like we have the Q value of this state, action up, Q value of this state, action left, and so on. What would be the action that the agent selects? What? Left, right? It thinks that by selecting left, it can get a total score of 4.2. So you just compare the Q values for all the 4 actions, check which one has the largest value, which is left. So you execute action left, and then what happens if you do that? What is the next state, and what is the reward that you're gonna get? So if I'm here and I execute left, what is the next state?
2.
Oh, it's 3, 2, and you would just go right and you go back and forth to maximize?
Maybe you penalized to
Yeah.
So
0.04. Doesn't look much.
I think I'm asking something a little. I understand what you're saying, but I'm asking something simpler.
Okay.
Where is the agent going to land if you select left? Where is the next state?
3, 2.
Always.
Oh.
There's a 80% probability that if I select
So then it goes
left, I'm
down.
gonna go here, but with 20% probability that action fails and I either go here or here.
Yeah.
Right? But let's suppose that in this specific run of the action actually succeeded and I ended up here. So now I have the other 2 variables that I need to know about. I know what S prime is, which is going to be 3, 2. And what is the reward that I get by being here? Minus 0.04, right? I'm penalized. So now I have all the pieces of information that I need in order to plug these values into that equation and do one step of update of Q-learning. And this is really low again. Anyway, so there are a few parameters of this equation that we have to tune besides these 4 variables. One of the parameters is this gamma value, which I discussed last time. Does anyone remember what gamma means?
I think it was how long you're willing to, or how many steps you're willing to take before getting the reward.
Exactly. Because, like, imagine that, so this is supposed to be the total score that I get, right? What happens if you set gamma to 0?
You don't consider any future steps.
Exactly. So, exactly right. If gamma is 0, all this expression is 0, and you're completely ignoring the rewards that can happen from the next state in the game. You only care about the reward that you got at that point in time. And if gamma is 1, that means that you're considering all the future rewards as being equally important to the reward that you got right now. And you can set gamma to any number between 0 and 1, depending on how willing you want your agent to be in maybe taking actions. Yeah.
Is there any situation where you would want to set gamma higher than 1 to consider future rewards more than your current?
Wow. I don't know, that's a kind of philosophical question. So, in what situation you would prefer to get rewards in the future instead of now? So like if I say you can get $10 now or $10 1 year from now, when would that make sense? It might make sense, but I never thought about that. That's a good question.
Maybe if the reward signal is really sparse.
If the rewards are really sparse,
And you only have 1 in a million rewards. So it doesn't work that often. So if it works, you want to have a bigger effect.
but then if you just set it to 1, yeah, I'm not sure. I have to think about that. That's a good question. But so okay, so but there's yeah. Go ahead, sorry.
The reward you get is changing all the time, collecting money to increase the value all the time.
Yes.
You might have to get it cheaper than right now.
If gamma is less than 1, you mean?
It might make sense to set gamma to higher than 1 if the reward of the person it's only takes every time value.
But that's what, if gamma is less than 1, then that's what happens. Your rewards, if I got a reward right now,
No, I think she's saying if the $10 you got now would as you get them, they mean less and less over time. But if you got them a year from now, they would be worth more than the $10 you got.
If you get like milk,
right?
one of milk every day rather than.
Okay, that makes sense. That makes sense. Yes, that makes sense. That's a very good example. Cool. But there's another complication of setting gamma to more than 1. Even though in that case, that's a really good example actually. But if you set gamma to 1, like let's say you live forever, you never die. What is the sum of rewards that you're gonna get for any action? It could be infinite, right? This summation could be infinite. And so it's kind of like a mathematical trick. It's like a hack that we set gamma usually to something less than 1 because otherwise the summations could be really, really large or infinite. But in that case, yes, that makes sense. So anyway, and the other parameter, so gamma is one of the things that you have to set. Alpha is the other one. What is alpha intuitively in this update equation? Like this is the new estimate for the total score. This is my current estimate, and this is like the new thing that I'm computing. So what is alpha doing? What happens if alpha is 1? Well, if alpha is 0.
Regulates how much weight you put on your current action versus the next actions.
Right. Something like that. So what? Let's suppose that alpha is 0. If alpha is 0, the second term is 0, which means that you're completely ignoring the reward that you actually got, and you're completely ignoring the state where you ended up. And so 1 minus 0 is 1, so your Q value doesn't change. You're not learning at all from this new experience. So alpha equals 0 is not very smart. What happens if alpha is 1? Then this term is 0. You completely forget what your current estimate is. So you've completely, maybe you already learned a lot about how much reward you can get. But you're going to delete that completely if alpha is 1. You ignore completely this, and your new guess is just going to be based on the specific reward that you got at that moment in time in the game. Which maybe you're just lucky to get that reward. We don't know. Sometimes, like, let's say you jump, and there was like a 1 in a billion chance that, like, you found $1 billion for some reason. But that's not very representative, right? We don't want to say, like, the agent to say, okay, this happened now, so it's always going to happen. And you completely ignore every single experience that you had in the past. So what alpha does is it regulates how much you're going to update your previous guesses, your previous estimates of how good that reward was, and your new guess based on this particular last experience that you had. Does that make sense? So you have to set those two things. So let's say that in this example I just arbitrarily picked alpha to be 0.5, so I'm going to combine this with equal importance, and gamma is 1 just so I get like easier to deal with numbers. So Q of SNA, this is my current guess for the total score that I can get at the state where I am in, and this is the action that I took. What is Q of SNA? S is the state where I'm in, and A is the action that I execute. What is this? It's 4.2, right? I was in this state and I took action left, so this is 4.2. R is the punishment that I got, minus 0.04. And then this expression, how do you compute this? Well, what is S prime? S prime is the state where I went to, which is this. To compute that max, I have to check all the 4 possible actions in the next state and see what is the largest Q value. So like the best possible score that I think I can get from this state. What is the max here? Max is 0.6, right? So that's going to be 0.6. And gamma is 1, so it's 1 times 0.6 plus the reward, which is this. I don't know how much that is going to be. But if you replace those numbers and compute that, you're going to get a new number, 2.38. So what do you do with this number? What is this? This is the new estimate for the Q value for this Q value, right? I was in this state and I executed the action left because I thought that this Q value was really high. And I have to correct this number because it's not so high. So I'm going to change this number from 4.2 to 2.38. Why is this Q value getting lower?
Because the reward you got for going left was way less than what you had originally assumed.
Exactly. Because you expected that you would get 4.2 total. But then what actually happened? You were penalized by like minus 0.4, and you ended up in a state where the best thing that you think would happen was getting 0.6. So that's way less than 4.2. So you have to lower this expectation. You have too high expectations here. So you're going to replace this with 2.38. That's one step of Q learning. And then what happens is the agent actually goes to that state and it repeats the process. So here the state would be 3.2. What is the action that it will take? Right, because that's the highest Q value. And what is the next state that it would result from that action? Again, it's kind of stochastic. With 80% probability I go here, 20% probability I go here, and like hit the wall and stay, and so on. But let's suppose, so we decided to execute right, because that is the thing that looked the best. And let's say that in this particular execution of that action, the action actually worked out, and I go to the right. So the reward is I got punished a little bit again, and the next state is 3, 3. I go back to where I was. And then you just compute the updated Q value. So you can compute this, and you're going to see that the new Q value is 1.88. Which Q value here is going to be replaced with this new number, 1.88? Yeah.
0.6, right? The one for moving.
0.6,
right.
exactly. So you always update the Q value of the state that you were in and the action that you actually took, because this is the thing that made you make this decision, and now you just realize. So the other question now is why this 0.6 was increased.
The expected value you can get from the next state is higher than that.
Exactly, because you expected to get total 0.6, but then what happened? You were penalized a little bit, but you ended up in a state where you believe that you can get 3.2, which is wrong, but whatever, that's your current belief, right? So, because you can't get 3.2 from here, but that's your current guess. And then you change this value, it goes up a little bit to 1.88, and then you keep repeating this process. So, if you run this for long enough, eventually all these Q values converge to the true values, to the true total reward that you can get, and then the agent actually knows when it is in some state. It really does know for sure the total reward that you can get for each one of the actions, and it just keeps greedily picking the action that is the best one. Yeah.
Once you hit your goal state, you just randomly pick another one and then keep going with the same values?
It depends. In most of the formulations, there's like this goal states where if you get to the goal state, you're just born again here or born again randomly somewhere. Yeah.
But why are we executing an action if we know that the value is not as desirable as it seemed before?
Say that again? Here we did pick the action that looked the best.
Yeah, but why we did it when we updated the value and suddenly instead of 4 it's 238 that we calculated.
Yeah.
And now 3.2 is much more desirable.
Yeah.
But why we executed an action to go to the other step?
In what update step? This one or the first one that I showed before?
First one.
So
here, from here. We know that 4.2 is good, right? Then we calculate the action value, which becomes 2.38.
no, you don't. Before you can only compute this after you actually execute left.
Okay.
Because you have, in order to update this, you need to know the next state where you ended up in and the reward that you got. So you can't know the new value before you actually try the action value. This happens after the execution of the action. And you keep repeating this process over and over again. Eventually all these values converge and so on, and then everything should work out. There is one problem here, which is, okay, you update that to 1.88 and so on. Now, this was a problem. The first step that I showed, the first example. The agent was in this state and it selected the action left, which was the wrong action, right? But it did select that action because it thought, based on these wrong Q values, that the action looked good. So, what is a risk that we could face if we just always pick the action that looks the best, that seems the best? But it's like you're making that decision based on these numbers which you know are completely wrong because you haven't learned the correct numbers yet.
You can end up in a local maximum, but you do have some stochastic probabilities of actually going different directions, so you kind of build that on it already.
Right. So the problem is, if you start with wrong estimates of the values, which is usually what happens because you're guessing them, right? What could happen is, like, imagine that you are in some state, like the state is you are in a restaurant and you have 4 different types of food that you can eat. And so you could eat like a steak or broccoli or some, or like, I don't know, grass, stone. And for some reason, when you are born, you think that eating broccoli is the best possible thing. Maybe you guys like broccoli, I don't. But maybe you are born with this belief that broccoli is amazing. And so if you just always greedily pick that action, you're going to keep eating broccoli forever. And you're never going to try anything else. So what is the solution? So how would you deal with this problem? What do you do? What do you guys do? This is an actual question.
Try something else.
You have to try something else. Even if you think, I don't know, like I don't have any good reason for believing that steak is good. It's just like this preconception that I have that it's horrible, but whatever, I'm gonna try it once to see what happens. And maybe it is going to be really bad, but maybe it's going to be really good. But from time to time you have to explore different things because you have to just see what reward you actually get. And that's a concept that is known as exploration in reinforcement learning. It's really important. Where you are in some state, sometimes, most of the time, it makes sense that you pick an action that looks good based on your experience. You can't just ignore everything. Like every time that I ate something like steak, it was good. And now I have the option of eating a piece of stone. I could do that. Maybe it's going to be better, but most likely it's not. But if I really want to make sure that the steak is the best one, eventually in my life I should try out these other crazy types of foods. So that's what they call exploration, and it's really required for this algorithm to converge. You need to explore and try new actions from time to time. So how do you do that? There are many exploration strategies that you could use. The simpler one is called epsilon greedy exploration, and what it does is something really simple. Where you are in some state, 90% of the time you pick the action that you think is the best based on your current estimate of Q. So like you go to a restaurant, you pick the food that you think is the best based on all the other times that you were in that restaurant. But 10% of the time you pick a random food in the menu and see what happens. Most of the time you're going to be disappointed, but there's a chance that you're going to find out something amazing and then you learn with this. Why did I decide that this is 90% and this is 10%? Well, that's a parameter of the algorithm. If you set the exploration rate to be 0, then you get back the greedy agent that never explores, and then you may always end up eating broccoli forever. And what happens if the exploration is 100%?
Just end up doing random stuff.
You just do random stuff all the time. So you actually do have the Q values for like how good each possible action food is, but you just ignore it, and every time that you go to a restaurant you just pick a random item out of the menu. Right? So the exploration is important. So before we go into the break, let me just show you a video of Q learning working on a few examples. This is like a maze that looks like the maze that I showed before, but it's larger. There's a +1 reward there, and this is the agent. And you get, I think here you get a -0.1 reward everywhere and a +1 there. So, and in this specific example, all the Q values of all the actions in all the states were initialized with zeros. So if the agent is here, for example, what is it going to do if all the Q values are 0? It's a tie, right? All the actions look equally good, so it just picks one at random. So that's why when I start the movie, you're going to see that the agent is moving randomly because all the actions look equally good. It's just moving around, exploring. Eventually, it's going to get lucky and find the reward by chance. Yeah. So when that experience happened, it updated the Q value of this state and action down. So now it knows that if it's here and it goes down, it gets some reward. But all these other Q values were not updated. They're still random or 0. So we need to now get to this state. When it gets to this state, then it checks, well, what are the possible actions? And then it's going to see, well, if I go down, I'm going to get a punishment, but I'm going to get to this state where I can get a large Q. So it sort of bootstraps faster as you start learning. Like the first time that you find the source of reward, then you can sort of propagate back that information to the Q values of the previous states. And this is the simplest version of reinforcement learning. Why do I say simpler? Because when you were in this state and you went down and you got the reward, you updated only this state, which is kind of not so smart because you could sort of have a memory of all the other states that I were in before, and I could propagate the information that there's a reward here not only to this state, but to all the other states that I had visited 1 second ago, right? So basic Q learning is like I take an action and I get a reward, and I assume that reward was just because of this last action that I took, which maybe is not really correct. It really depends on all the actions that you took before. But if you keep running this for long enough, eventually it figures out. Any questions?